All right, let's rock. Let's look at the double angle identities. Surprisingly enough, the double angle identities are actually just based on these guys right here, and of course the Pythagorean one, which says the sine squared of a plus the cos squared of a equals to 1. All of them are dependent on that. It's really, really quite simple. Look, if I give you the sine of 2a, what are we actually doing here? We're actually taking the sine of a plus a. Well, isn't the sine of a plus a just this double angle identity? Of course, this would make this the sine of a, the cos of a, plus the cos of a, the sine of a. Every angle is a here now. So wherever you saw b, just put an a. All I did was rewrite this, right? So look at this. Isn't this sine a cos a? Couldn't this be written backwards as sine a cos a? So look what you got. You got sine a cos a plus sine a cos a is 2 sine a cos a. So there's your first double angle identity. Oh my goodness, this makes it so nice because think about this. If you have this in your back pocket, you don't really need to go back and start doing all that craziness with the double angles, right? Yeah, you still do, but this makes it a little bit easier. Take a look at the next one. Same idea for cosine. Check this out. Cosine of 2a. Is this not just cos a plus a? Right. So a plus a is going to be this one. There's your a, giving you cos a, cos a, cos a, cos a, right? Minus sine a, sine a, sine a, sine a, because all of b's are replaced with a. This is cos squared a minus sine squared a. Very, very Pythagorean, very close to being Pythagorean. The difference is it's a subtraction. Well, that's because this is double angle. Same goes with the tangent. Tangent can be done the same way. All you have to do is, again, put in a plus a. And wherever there's a b, just replace it with an a. Look, a plus a. So this is now tan a plus tan a. Well, isn't that just plain old 2 tan a? Isn't this 1 minus tan a times tan a? Isn't that tan a squared? Yeah, no kidding. Real simple. Okay, so how do you use these things? Well, that's what this next question's all about. Check it out. Look, here's all our double angle identities. There's the sine one. There's the simple cosine one that we figured out, and there's the tan one that we figured out. But wait a second. Cosine, for some reason, has 2 additional ones. Well, if you think about it, they're all based on the Pythagorean theorem, right? The idea that cos squared a plus sine squared a equals to 1. So look at the variations. Right? If you look at the variations, you know that sine squared a equals to 1 minus cos squared a. And so all they did is took this and substitute this in for the sine squared a. So now you got cos squared a is 1 minus cos squared a. And it's, of course, a negative. This gives you this wonderful thing. Same thing goes if you do the opposite and go cos squared a equals to 1 minus sine squared a. You take this guy right here and throw it into there. Whoa, right into there. You get this guy. All it is a variation. So honestly, you're probably saying to yourself, well, sir, which one do I use? Well, honestly, the most common one to use is this one right here. That's really the most common one. If you ever have to put the Pythagorean one in, just throw the Pythagorean theorem one in there. Okay? You don't have to worry too much about these two things. Okay, so let's go. Let's use it. Check it out. Check it out. It says, consider this identity where sine 2x over 1 minus cos 2x equals to cotangent x. Well, before we even do it, let's talk about the non-permissible values. First things first, you know and I know, yep, 1 minus cos 2x cannot equal to 0. Bring that 1 over, you got minus cos 2x cannot equal to, yep, minus 1, which leads you to cos 2x cannot equal to 1. Now, we did this one in the last podcast, but just in case you don't want to flip back, I'll do it again. It's very important to realize, again, that we have to look at the double angle identity here. Okay, don't forget, you have a beautiful idea of this double angle. Let's look at this in terms of a simple 0 to 2 pi, right? Okay, now remember, this is no longer just x, it's 2x. So we have to look at it from 0 to x to 4 pi. Okay, what does that mean? Think about it. Where is cosine 1? Tell me, where is cosine 1? Let's figure that out. Cosine is 1 right here. Cosine is 1 at 0 pi and all the way up to 2 pi. There's your first circle around to 2 pi. Okay? Your next one, though, is remember, we are going a double rotation. Double rotation. And the reason why we do a double rotation, okay, is because of the fact that this guy is 2x. So we do a second rotation and we find out, okay, not only is it 0 pi, right, 0 pi and 2 pi on the first rotation, but it goes all the way up to 4 pi in our last rotation. Beautiful. Now, so that means then you've gotten rid of the cos. So the cos, then the 2x, I should say, the cos is gone. The 2x is 0 pi, 2 pi, and 4 pi. So check this out. Just divide by 2. Divide by 2. So that cancels out, giving you x can be equal to 0, pi, or 2 pi. And that's our actual answers. All right. So what does this mean with our non-permissible value then? Our non-permissible value then is, look at this, a multiple of pi. Yes. One of our non-permissible values then is n times, pi, where n is an element of I. Whoa. Wow. Okay. Now, before I go on, there's still one more non-permissible value here that we got to figure out. Do you see it? Wait a second. I'll show you. It's right here with cotangent. Remember what cotangent is. Tangent is sine over cos, so cotangent is cos x over sine x. So guess what? Your sine x cannot equal to 0. Where is sine equal to 0? Yep, here and here again. Ah, great. So again, you're still looking at multiples of pi. So you got it covered right there. Your multiples of pi. So that means x cannot equal to some multiple of pi, n times pi, where n is an element of the integers. Got it? Whew, that was a lot of work. All right, now I want to verify something. I've told you that this guy up here is in fact an identity. All right, so I want to verify this identity numerically using pi over 3. Well, you know, that's actually pretty easy to figure out. All you have to do is substitute in pi over 3 here, here, and here. Okay, so let's do this. Sine of 2 times pi over 3 over 1 minus cos of, 2 times pi over 3. Now, think about this. All this works out to be, if you think about it, this becomes, sine of 2 pi over 3 over the 1 minus the cos of 2 pi over 3. Okay, let's be smart here. Let's figure out what 2 pi over 3 is so I can figure this out real nice and simple, yippee skippy. Okay, looking at our unit circle. 2 pi over 3 is that thin one right there. That's the 2 pi over 3, right? What are the coordinates? The coordinates of that, of course, are going to be minus a half root 3 over 2. Okay, so there's your sine, there's your cos. So your sine of 2 pi over 3 is going to be, root 3 over 2. This cos one is going to be minus half. So you got 1 minus a half. Okay, that's 2 over 2 then, right? 2 minus a minus 1.5 is, okay, add those together. Look what you got. You got root 3 over 2 divided by, that looks like 3 over 2. Okay, root 3 over 2 divided by 3 over 2. Looks an awful lot like take the reciprocal and multiply. Oh my goodness. Look at that. The 2's cancel out, leaving you root 3 over 3. There's your answer. Okay, now my question, or the question that was answered here or asked here, was does that equal the cotangent x? Well, yeah, it's simple to figure out because cotangent, remember, is cos x over sine x. Well, what was x? I told you to try pi over 3. Okay, so what's cos of pi over 3 divided by the sine of pi over 3? Okay, where's pi over 3? Well, I just happen to have it right here. Pi over 3 is still dealing with this guy for some odd reason. There's 1/2 root 3 over 2. Okay, so we're looking at the cos of pi over 3 being 1/2. We're looking at the sine of pi over 3 being root 3 over 2. So good. 1/2 divided by root 3 over 2 is the same as saying 1/2 times 2 over root 3. Look at that. Those guys cancel and 1 over root 3. Now, I know what you're saying. Those two don't look alike. Well, actually, they do. What you have to do is rationalize the denominator. Multiply the top and bottom by root 3. This is a math 20 step here, leaving you with root 3 over root 3 times 3 is 3, and they, in fact, do equal. Oh, how sweet. Now, here's the next thing. We're going to use technology now to prove and verify this identity. So, just like we did before, let one side be y1, let's the other side be y2. Okay, hold. So I rewrote the identity here and cleaned things up. And here's y1, there's y2. I'm just going to throw that directly into my calculator here. Okay? So I'm just going to put this into my calculator like using the alpha button. Of course. Second alpha, there's their fraction. So put in sine 2x. Oh, that's not very tough. Underneath here, you're going to put down 1 minus cos 2x. Oh, how beautiful is that? There's your y1. Your y2 is cotangent x. Now think about what cotangent x is. There's a number of different ways you can write cotangent x. You can write this as cos x over sine x. You can write it like that, or you can write this as 1 over, yeah, tan x. Oh my goodness. I kind of like this. That to me makes a lot more sense. So, okay, alpha, all right, F1, find my fraction, throw it in there as cos x, boom, over sine x. Look at that. Perfect. Excellent. Okay, let's clean this up. Now, remember that you are doing this over an identity. So let's put this into radians. Well, yeah, okay, here's my calculator in radians. Everything's good. What's my next step? My next step is to make sure that my windows are set up properly. Real simple. Hit zoom, and down here you'll notice a number 7 is trig. So just hit zoom and 7 and watch this. It pops up just beautifully with all the trig values in there in radians. Boom. And there it is. Look at that mess. Oh my goodness. But look at that. Why did that happen? Why did I have a blue line and right over top of it the red line? That tells you right away that these two lines are exactly the same graph. That proves that it's an identity graphically. But look at this monster coming up. Uh-oh, let's prove this identity algebraically. Oh no, oh yes, that's where the mess comes in. Okay, so what do? I need my identities, of course. Yeah, okay, here is sine 2x. It's the only one you've got for sine 2x. So real simple. You're going to go, okay, for sine 2x, you're going to go 2 sine A cos A. How nice. And then this is 1 minus cos 2x. Well, like I said before, use this. That's the easiest one. 1 minus, okay, so just put it in. Just put it in. That's what cos 2x is, so just put it in. Here we go. Ready? This is going to be cos A cos squared A minus sine squared A. Look at that. Isn't that pretty? Oh, yeah. I know you're saying, oh, it's pretty ugly right now, sir. Yeah, don't worry about it. Watch. I'm going to show you how to do this. Real simple. Honestly, look. Distribute. What do you get? You got 1 minus cos squared A plus sine squared A, right? Now, remember what we did about 6 or 7 podcasts ago? Remember this guy? You seen it before? You should have seen it before because check this out. This is so cool. Ready? Sine squared A plus cos squared A. Watch this. If you take this cos squared and remember to bring it over to the other side, you get sine squared A equals to 1 minus cos squared A. Oh my goodness, there it is. Oh, look at this. So put the sine squared A in for this one. So now think of what the denominator is. The numerator hasn't changed. This is 2 sine A cos A all over. Oh, look at this. This is now sine squared A plus another sine squared A. Doesn't that give you 2 sine squared A's? It does. Now check this out. My favorite part. Things can cancel. This is gone. And look at that. A sine A is gone with one of these. So what do you have left? You have cos A over sine A. Now wait a second. Oops, sine A. There we go. What is cos A over sine A? Cos A over sine A, isn't that cotangent of A? Yup. What was the original question you were trying to find? Oh, look at that. You wanted it equal to cotangent of A, and it's exactly what you got. You got cotangent. There it is. You've proved it. Now, if you want to be really cool after you've proved an identity, you put a little square down like this and you shade it. That just says, I'm done, baby. I proved it. And people at the math parties, whoa, they're just going to freak out when they see this one.